today we're going to talk about rotations in the coordinate plane, and I am using a platform that might mess my presentation up. As a matter of fact, I know for a fact my presentation is a little off. Don't worry, we're going to talk through it. This takes visual learners, and there's also formulas for those people that are like myself and we cannot see things visually. All right, so rotation. It's a transformation in which a figure is turned about a fixed point called the center of rotation. So we're going to pretend like this happy face is the center of rotation. I'm going to tell you right now it's going to move a little bit, and we're not supposed to move it, but we just want to see what happens to my point as it moves around. And so here we have it. There's moving. Looks like about 90 degrees, and then here we go back. Rays drawn from the center of rotation to a point in its image form an angle called the angle of rotation. So here's my angle, well, here's my center of rotation here. This point is called the center, and here's the point that I'm rotating. So the point, the center of rotation, and the point that I'm rotating. Those dots are doing what they want to do. This G prime represents, so we'll put a little dot there, represents the transform point. So it started here and it rotated here, 90 degrees, about this point. A rotation is an isometry. The segment lengths are preserved, the angle measures are preserved, parallel lines remain parallel, and orientation is unchanged. So rotation is on the coordinate plane, so we need to make sure we understand and know the formulas for 90-degree rotation, 180-degree rotation, for clockwise and counterclockwise. And also, unless, and I'm sorry if you can't see this, but I'll read it to you. It says, unless told otherwise, the center of rotation is the origin at 0, 0. And here's our origin, 0, 0. All right, so clockwise formula, 90 degrees clockwise, the formula is to switch the x and the y value and to provide the negative or the opposite sign for my x value. So here I have a is at -2, 4. If I want to rotate this clockwise from the origin, here's my point origin here. If I want to do it clockwise, then I am going to move it 90 degrees. And it's hard for me to visualize what that 90 degrees look like. That's why this formula is so important to me. And there it is. There's my 90 degree. There's my new point. And it's going to come right there. And so my new point will be, my y will come first. So it's going to be 4. And my x is going to change sign. And it'll be 2. So this looks like it is at 4, 2. And there it is. That ball is going to do what it wants to do, but we know that it lands right there at 4, 2. All right, the next, same thing, same formula for 90 degrees clockwise. We have -3, -2. So again, we know my y will come first. And my x will change signs to a 3. So that's going to give me at -2, 3 up here. So if I'm going from here, rotating, it should rotate right there. There we have it. -2, 3. Now clockwise, the formula changes a little bit. The y still comes first, but this time this is the one that changes direction. And again, recall, here is my clock. And so we know clockwise is going in the same direction that a clock will go. Well, counterclockwise is just like what it sounds like. It's going to go in the opposite direction that a clock will go. So if I have 4, -2, I have my y value is -2. It's going to change signs. That's going to become a 4. So I will be at 2, 4. And there is my new. So from here, from 90, I'll go to here. There we have it. That counterclockwise. All right, another example of counterclockwise. So again, my y value will come first, but it'll be the negative of that. And my x value will take the place of my y. It's going to keep the same sign, just the formula that I'm plugging in. And I will have 1, 2, 3, 1, 2, 3, 4, 5 down here. So from here all the way down here. And that ball is just doing what it wants to do, and it's okay. We know that this is the point that it's going to reach. All right, so now 180-degree rotation. If I'm going into basically 180 degrees is a straight line. So that one is probably the easiest one to visualize for myself. I'm sorry, I went ahead and hit the button by accident, but we have it at 1, 2, 3, 4, 2. That's 180 degrees from here to here. That's a straight line, right? And the ball just doing what it wants to do, but we know where it's supposed to land. Again, our formula for 180-degree rotation is just to change the values, to change the signs. So we'll have -3 and +4. So we go over to 1, 2, 3, 1, 2, 3, 4. Oops. So from here to here, it definitely looks like a straight line. Oh my goodness. There it goes. Come on, ball. Do what you're supposed to do. All right, so now let's talk about, for the most part, when we see things, we don't just see a point, we see an entire image. So here we have a triangle. So it says draw a coordinate grid and graph -3, 0, -2, 4, and 1, -1. Then draw a triangle ABC. So -3, 0, -2, 4, and 1, -1. All right, then I drew the triangle. Then it says rotate triangle ABC 90 degrees counterclockwise. And remember the formula is y -x. So the first one, my y is going to take the place of my x, which becomes 0. My x will take the place of my y, and it changes sign. And so there it is plotted. Here, remember it's clockwise. And so again, for B, it becomes -2, 4 becomes 4, 2. And then for C, we have -1, 1, -1 becomes -1, -1. Okay. Then we can check by rotating. Of course, this is not going to rotate correctly, but if we know that if we rotate it 90 degrees, that it should rotate directly onto the triangle that we just made. Okay, I don't know, so just pretend like it did it the correct way. All right, so again, here are the formulas. 90 degrees clockwise is xy becomes y -x. 90 degrees counterclockwise, xy becomes -yx, and 180-degree clockwise becomes -x, -y. Rotating through an angle other than 90 or 100 requires much more complicated math. Or we can do compound reflections. And so that's one thing that will help us out a lot. So if lines K and M intersect at point B, then reflection in K followed by a reflection in M is the same as a rotation about point P. Here's an example. If I say rotate it, let's say, for example, 90 degrees about point P, and then again 90 degrees, a reflection followed by a reflection about M. Again, I can combine those reflections together. And so furthermore, the amount of rotation is twice the measure of the angle between lines K and M. So if they're 90, if they're 45, excuse me, then they'll turn to 90. And again, I am not very good at visualizing, but it is definitely not 90, 90 because that would look like 180, so I apologize. So yes, definitely 45 to give me All right, so rotational symmetry. It says a figure can be mapped onto itself by rotating a rotation of 180 degrees or less. So basically we're looking at different figures and see if they have rotational symmetry. And so this figure, can it be rotated onto itself? Well, absolutely, it's a square. If I rotate it 45 degrees, it's not going to work though, of course. But if I rotate it 90 degrees, these are exactly the same. So this is a 3D image. So starting here and I rotate it, 45 we saw that it didn't work, but 90 degrees works. So a square has a rotational symmetry of 90 degrees. Does this figure have a rotational symmetry? Let's see. All right. So looks like the hexagon has a rotational symmetry. It's off by a little bit because it's a little extra rotated, but it's a rotational symmetry of 60 degrees. All right, does this figure have a rotational symmetry? I'll rotate it 90, then 180, looks like. It has a rotational symmetry of 180. Does this figure have a rotational symmetry? Rotate it 90 degrees, there is straight up and down. Then 180, it's upside down. Then another 90. That's 270. So no, it doesn't have 270. It has to be rotated all the way around. So this one does not have a rotational symmetry because you have to map it all the way back. You have to go all the way in a full circle. So that is not rotational symmetry. All right, so rotating segments. Again, this is going to be off a little bit because of the 3D way that it looked, but we can also use our knowledge of our formula also to help us. So it says rotating AC, and this is line AC, about the origin maps it to 90 degrees. And so remember 90 degrees, so let's take A for example. So A is at 1, 2, 3, 4. So this is -4, 0. And C is at 1, 2, 3, 4. So this is at 0, 4. Well, we know when we map 90 degrees, it's going to be the y (-x). So this becomes, A will become, I'll write it over here so I don't, will become 0, 4, which is at C, right? So 0, 4. And C transform will become 4, 0. So 4, 0 is here. So here to here. So that will be CE. All right, rotating 90, HG 90 degrees counterclockwise about the origin. So HG is from here to here, and H is at, let's see, 1, 2, so -2, 1, 2. So H is at -2, -2. And if I do a counterclockwise of H, that is going to give me the opposite y, which is 2, and the x, which is -2. And what point does that take us to? To -2. We have 1, 2, 1, 2, so it comes over here. All right, G is at 1, 2, 3, 4. So this is at 0, -4. Again, the formula for counterclockwise is going to give me 4, 0. Where's 4, 0? 1, 2, 3, 4. Did I do that correctly? No, couldn't have. Let's see. 1, 2, 1, 2. Nope, sorry, rookie mistake, not there. 4-0. I apologize. I am all the way out. Let's see if that's correct. All right, yep, looks like it. We are at FE, so it stops at FE.